We are Group 20, the Advanced Breadboard, and this is our final demo. Here we have our three main engineering specifications that we will be demoing in the videos to come. First is checking the time between the software and the hardware interacting. The timer will start as soon as the user presses the translate button, and then the LED should activate. A button will appear for getting the current and voltage data, and once that button is pressed, those values should be presented, and that will be the end of the timer. For the open and short circuit detection, we're going to show a couple different circuits where we're going to go ahead and make an open or a short, and the GUI should give a warning to the user that there is an open or short circuit detected. Finally, there's a LED activation placement. If the algorithm decides that these certain LED nodes should be activated, then the corresponding LEDs should activate properly.
So this is our advanced breadboard hardware specifications. We're going to be showing you all the hardware components and how they connect with each other. So over here, this is our PCB for the advanced breadboard. We have connected are the LEDs, the ESP32, two buttons, the INA 219, which is the current and voltage sensor, and then the voltage regulator, the TPS 61023. In the back of the PCB, we have the switch and batteries connected for easy access. So with this, what we have is these 4 pin headers, which are connected to the ESP32. This will be used to connect to the RS232, which is then connected to the Raspberry Pi over here. The RS232 is responsible for the communication between the Raspberry Pi and ESP32. That's how they will be communicating with each other, turning on and then that's where the communication will be sent over to the ESP32, and then the LEDs and sensors will be programmed through there. On this left side here, these are all connected to the sensors. 2 pins, that's used for the user's power supply. This is V in, and then the ground. On this other side of the 2 pins, it will be the ground, and then that will be connected to the load circuit or the user circuit. What we have over here is a power supply that the user could be using. We're going to be using this to kind of use our test runs to demonstrate the user's power supply. And that is how all the communication for the hardware is connected.
Here we have a full software overview, and so as we can see here, this is what the GUI would look like, and you would be introduced to a lot of components that you can use. For example, a resistor, ground, DC power source, capacitor, and you would use the wires to connect each component to wherever you want them to. You also have the neat little reset function, which gets rid of all the components on your canvas, so that way you can restart and reset all your connections. As well as you can use an inductor, for example, and you can use a junction. Now, a junction allows you to connect 2 or more components to the same node, and a ground works similarly to the junction, as it really just acts as a label more than an actual component. We also use toggle labels there to toggle whether you want to see the actual values of each component or not. It's really useful if you don't really care much for that and more want to just see how the components look like together. And once you make your circuit, you can translate that, and as you can see, the bottom left and right nodes show A and B, and or A and D, and it's going to show you the connections you need.
This is our first trial run for how we're going to be doing this. As you can see here, we have the GUI. We're going to create a circuit with 2 parallel resistors. So I'm going to include a DC power source. I'm going to connect 2 resistors. So since they're going to be in parallel, we're going to use the junction feature to kind of connect these resistors together. So junction, and then the last component would be our ground. So then we will use the wire to connect our voltage source to the junction, which connects to the resistors. Both resistors connect to ground, as seen below, and then the voltage voltage source connected to ground. Now after this, what we're going to hit is we're going to click translate. Now, node A and node D are on. Node A is light green and node D is red. And as you can see here, these 2 nodes are on, telling us that this is where we need to connect the resistor and our voltage source. So this right here is our load in, so positive. I'm going to connect the resistor here to here, as seen. And then the second resistor is going to be connected here, as well as here. and then the ground will be connected to node B. So you can see that it's shown here. It says use V1, R1, R2 connected to node A, and then node D would be R1, R2, and ground, and that's exactly what we did here. Then we need to test if we're going to get, we're turning on the voltage source right here. So this is the user's power supply. So you can see that we're 5 volts and drawing out 6 milliamps. Now we're going to go ahead and see if we have an open circuit or a short circuit. Get sensor data. It's going to take a second, but you can see here the sensor is reading 5 volts and the current is 5 milliamps. Now we're going to show you what's going to happen if we disconnect and have an open source. So we're going to disconnect the negative node, and now we're going to click again, get sensor data. As you can see, potential open circuit happened here. In trial run, circuit is built on here. We're going to hit translate. Node B and A are on. V1 and R1 is on node A. So V1. Okay, and then this is ground. We're gonna get the sensor data. 3 milliamps is how much we're getting with 5 volts, and that is showing on the power supply. We're going to go ahead and open the circuit, get sensor data, potential open circuit. Third trial, and this is going to be a very complicated circuit that we're going to draw out. So what we have here is a voltage source, 2 parallel resistors connected in series with 2 parallel capacitors, which is connected in series to 1 resistor connected to series in 1 resistor, and that is being grounded. So this is how it would look like. We need to add 4 junctions. So these 2 resistors need to be connected by this junction, and then this junction in order to connect to these 2 capacitors connected to this junction and this junction here. So we're gonna hit translate. So we can see 1, 2, 3, 4, 5 LEDs have turned on, and we're gonna go ahead and connect them based off that. We can see here that V1 is at node D, which is down here, and then ground would be at node B, which is over here. Okay, so you can see that we used 5 LEDs here for 5 nodes, and we connected them here depending on by the instructions mentioned in the GUI. Now we're going to go ahead and get sensor data. You can see here that it is saying it's an open circuit because we're using capacitors in DC voltage source. So as soon as they get powered up and charged, it would imitate a open circuit, which is why our warning says a potential open circuit, even though it's not. That's all. So for this trial run, we're just going to go ahead and try to test for a short circuit. As you can see, we're just going to go ahead and build a simple circuit on the GUI with a resistor and DC voltage supply, and click translate. As you can see, the yellow and green LED is supposed to be on, so that's where you see that's on, and we're just going to connect the circuit as usual. Add the resistor on there. Now we're just going to go ahead and click get sensor data. As you can see, we're getting 12 volts with 6 milliamps and no warning, so everything's working as intended. We're going to go ahead and try to short the circuit, as you can see here, and then get sensor data. As you can see, it says potential short circuit, and although the voltage sensor reads a voltage of 0.14 volts, it still falls within the threshold of an open circuit, since we can never get 0 volts with the sensor that we're using. So what my teammate Sheridan is doing here is she's going to be running the software and test how fast the software takes to send the information to the PCB and turn on the lights. And then we're also going to click get sensor data and see how fast it takes for the sensor to send that information to the ESP32 and back into the GUI. So we're going to go ahead and click translate. And you can see it took 3.5 seconds to get the LEDs to turn on. And then at 7 seconds, the sensor data was sent over. So we can say that it took about 3.57 seconds to get the sensor data back into the GUI. So additionally, we ran 5 more trials to kind of get an idea of the average software runtime, open short circuit accuracy, as well as the LED activation accuracy. You can see after these trials, we have an average of 6.82 seconds for the total software runtime. We have an open short circuit accuracy of 80% for an open and 100% for a short. For the open circuit, you can see in trial 4, we did use a capacitor in the circuit, and the software did come back and say that it could be a potential open circuit, which is not completely wrong considering the fact that as the capacitors are charging, they do act as an open circuit. And finally, for the LED activation, we saw that there was a 100% LED activation accuracy. And that concluded the trial runs for our experiment. This concludes our final demonstration video, and we'd like to thank you for watching, and we look forward to seeing you in the live demo on Tuesday. Thank you.